Okay. Yeah, so in this presentation, we're going to start off with an overview of chip firing games, which is what Shefali just talked about before. We're going to discuss some upper bounds and higher gonalities and an application of that upper bound improving an NP hardness result. And then we're going to conclude by discussing some lower bounds and higher gonalities. So again, an introduction to chip firing games. We're going to have a graph, and we're going to define a divisor on a graph as throwing down poker chips on the vertices, just as Shefali was saying. So if we're given a graph, we can say, okay, let's put down two vertices or two chips on this leftmost vertex. And then we get this wonderful divisor where we have two chips on this leftmost vertex and then 0 chips everywhere else. Further, we can define what is called a chip firing move, where if you're given a chip firing move on some vertex, essentially just changes a divisor by sending a chip from that vertex to each of its neighbors. So if we fire this leftmost chip right here, we can get this following divisor as it sends one chip to each of its neighbors. And now we're going to talk about the lovely gonality game, which is played with chip firing moves. And this is going to be the first gonality game. So again, we're given a graph and we have 2 players. Player A is going to put down K chips on graph G. Player B is going to get -1 chips. They're going to put it down wherever they want on the graph. And then player A is going to chip fire a bunch of vertices, and they're going to win if they can eliminate debt, and then lose if they cannot eliminate debt. So if they're able to chip fire to the point where no vertex has negative chips, they win. And we can play the gonality game on this same graph. Let's say player A put 2 chips on this leftmost vertex, and then B put a negative chip there. We can see that player A can actually fire this leftmost vertex, just like we did before, and get this new divisor. And then they can cluster fire these 3 vertices in red, and cluster firing essentially moves cancel out. So if you have 2 vertices that fire at the same time that are connected, those chips will cancel out. So it'll only send chips along edges that are going out of this vertex set. So if we fire these 3 chips or these 3 vertices, we get this following divisor where debt is eliminated and player A wins the gonality game. And you might be wondering how the heck we figure out which vertices to fire. There's so many possibilities. How do we eliminate debt? And that's why we have Dar's burning algorithm, which actually determines and gives you a roadmap to winning a gonality game if you can actually win it. And the way that Dar's works is you start a fire at vertex Q, and Q has debt on it. You let that fire spread through the graph according to rules. So if an edge is connected to a burning vertex, that edge burns. And if a vertex has more incoming burning edges than it does chips, that vertex burns. So you can think of chips as sort of firefighters in this situation. And finally, when the fire stops, you chip fire these unburnt vertices. And if the entire graph burns, that means that you cannot eliminate debt. But chip firing these unburnt vertices will eventually, if possible, lead to eliminating debt. And we can run Dar's burning algorithm on this same example just to see how it works. We burn this first -1 vertex, and then these edges incident to it burn. And since these vertices that are connected to burning edges have no chips, they also burn, causing more edges to burn. But you can see that this leftmost vertex has 2 chips and 2 incoming burning edges. So that vertex is actually protected and will not burn. So we can fire that vertex, we get this divisor, and you can see that the fire then stops here. We can fire these 3 vertices to result in a positive divisor, where you can see that player A wins the gonality game. And now we're going to discuss higher gonalities, which is where it gets fun and what we're really focused on this summer. And it's essentially the same as the first gonality game. However, instead of placing -1 chips down, player B now has -R chips to place on the graph. And it's the exact same process, but just with that slight change. And we call the orthogonality of a graph the minimum number of K chips player A needs to always win the gonality game, no matter what player B does. And the complication with higher gonalities is that once player B gets more than 1 chip to place, or more than 1 negative chip to place, there are a lot more possibilities. So for example, player B could put -2 chips there, or they could distribute them along some other vertices, or they could even put 1 somewhere else and then 1 on top of a chip that player A has already placed. And for upper bounds on higher gonalities, the only one we really know is trivial, and it's based on first gonality. So if you take the winning divisor for first gonality and put it on the graph R times, you can play the first gonality game R times to eliminate R units of debt. So for example, if we have this lovely graph that we've been working with and we want to eliminate 2 units of debt, we can just put it down again and we'll have 4 chips and we can play the second Gonality game twice. However, this bound isn't exactly sharp. So we use the K independence number, which is the maximum size of a set where any vertices are greater than K distance apart, to discover or to prove this new upper bound for graphs with minimum valence greater than or equal to R and girth greater than R+1. And we actually construct a divisor using this independent set to prove that the orthogonality is less than or equal to n minus this R independent set with graphs with these restrictions. And we can look at this theorem in terms of R equals 2 to kind of gain some intuition for why it works. So for R equals 2 for second Gonality, this theorem gives for a triangle-free graph with no leaves, we're going to have it bounded above by n minus the second independent number. And we can use the crown graph on 10 vertices to see this in action. So we can clearly see that the second independent set in this case are going to be 2 vertices that are directly across from each other. So these 2 zeros right here. And we're going to construct a divisor by essentially putting zeros on this independent set and then 1 chip everywhere else. And then we can go through some possibilities of what player B might do to show that our restrictions actually ensure that player A can win the Gonality game. So player B could, for example, put chips down on these independent set vertices. We can run DARs. We can see that these two negative chipped vertices will burn and their edges will burn. But since we have an independent set, we know that first, every neighbor of one of these negative vertices has 1 chip, and second, neither of these negative vertices share a neighbor. So no more vertices will burn. And because of high valence, we can fire unchipped vertices to result in a positive divisor where there is no debt and player A wins the Gonality game. Second possibility is where player B puts 2 chips or any sort, their 2 chips on positively chipped vertices. So in this case, they put 2 chips, negative 2 chips on a vertex with value 1. This burns right there. And then we can see that's actually connected to a vertex of value 0. So that vertex will burn, sending more edges out. But since there are no triangles, and again, we have the second independent set, no more vertices will burn. And because of high valence, we can see that firing these unchipped vertices will result in a winning placement. Now, this process generalizes to R greater than 0 to produce the best known upper bound on higher Gonality.
Great. So now we're going to discuss an application of our new upper bound to the NP hardness of higher Gonality. So we proved that it's NP hard to compute second multiplicity-free Gonality. So let's first define multiplicity-free divisors and Gonality. So we say that a divisor is multiplicity-free if on every chip or on every vertex, it places 0 or 1 chips instead of kind of 2, 3, or any more. So we've actually seen multiplicity-free divisors in our proof before. That Gonality 2 was less than or equal to n minus alpha 2 with the crown graph. And this will be kind of important later on in our proof of the NP hardness. And we then say that the second multiplicity-free Gonality is the minimum degree of a multiplicity-free divisor of rank greater than or equal to 2. So this summer, we proved that it is NP hard to compute multiplicity-free second Gonality, even for simple connected bipartite graphs. And this kind of second half of the theorem, even for simple connected bipartite graphs, is rather important since for bipartite simple connected graphs, a lot of NP hard problems are still kind of easy or polynomial time to compute. But for multiplicity-free second Gonality, we show it's difficult even for these sort of simpler examples that exist in the family of all graphs. So I'll go over kind of the main steps of the proof. So it's a reduction proof from the alpha 2 problem that we saw earlier. So the first thing we're going to do is create a graph G hat, which we call the bipartite extension, from a 4 regular bipartite graph G. So on the left here is kind of an original graph G that we would have, 4 regular bipartite. And what we do is we kind of make copies of this, the edges between B1 and B2 also exist between B1 and A1. So all the edges between B1 and B2 are now also between B1 and A1, and same between B2 and A2. And then we kind of connect all of A1 and A2, creating a complete bipartite graph. And the key is that we'll see in the next few slides, but the distance to independence number will stay the same, but we can kind of use this graph to match a lower bound with stars. So as I indicated before, kind of we have that the distance to independence number stays the same. What we say next is we have an upper bound, which Lizzie showed us, of kind of the number of vertices minus alpha 2. You might wonder, well, the upper bound you gave before kind of applied for second Gonality. Can we use it for multiplicity free? And the answer is yes. And the reason is kind of in our proof for Gonality to upper bound, we constructed a multiplicity free divisor. So luckily it all follows through with this upper bound. Now we can use Dar's burning algorithm, which we presented before, to match the lower bound to the upper bound for our bipartite extension G hat. And kind of on a high level, what we do is it's a proof by contradiction. If we have less than that number of chips matched by the upper bound, we can find a burning component, this sort of path that, for example, can look like 0, 1, 0. And we can argue that an adversary will clear out the 1 from this path and use another chip to kind of burn this component, creating a -1, which will burn the whole graph. And then we match our lower bound to our upper bound. And finally, what we can say is, since alpha 2 is NP hard, even for simple bipartite graphs, so is the second multiplicity free Gonality. That's because this step 5 gives us an easy way to compute alpha 2 if we know how to compute second multiplicity free Gonality. So if alpha 2 is hard, then multiplicity free Gonality must be just as difficult. So yeah, this proof kind of has two important takeaways. First, it's an important result in sort of the complexity theoretic standpoint, but also it shows that our upper bound is useful in kind of unlocking new problems that we can look at for multiplicity free Gonality. Now, in the last few minutes, I'm going to kind of briefly introduce lower bounds for higher Gonality. So for first Gonality, we have kind of a framework under which lower bounds have been developed. But for higher Gonality, the best lower bound we have kind of trivially depends on lower bounds that exist for first Gonality. And these lower bounds that exist are rather weak. So what we do is we extend a notion of the scramble number for first Gonality, where scramble number is one of the best, or the best, but not one of the best based on the work done by Liz and Lisa. Lower bounds for first Gonality. And what we did is we extended this to higher order scramble numbers. And for those familiar with scramble numbers, what we did is we created a 2-hitting set component within scramble number instead of just using the 1-hitting set that existed for scramble number. But for those not familiar with scramble number, the takeaway is we've developed a lower bound that is much better than that existed for first Gonality and could be extended to higher Gonalities. And yeah, this lower bound won't depend on lower Gonalities as well. And it's, yeah, as I stated, a far improved lower bound to the trivial ones from before. And now, just in conclusion, in this talk, we've presented some of our work this summer on lower bounds and upper bounds and complexity. So we've developed the best upper bounds so far on higher Gonalities. We also showed that we can use these upper bounds for complexity results. And lastly, we developed non-trivial lower bounds for higher Gonalities that kind of extend the framework for lower bounds that we had for first Gonality in a natural way. And we also want to say thank you so much to our advisor, Ralph Morrison, for his tremendous support and guidance, and to all the other researchers in the Chip Fair and Games group. So Jason, Iobel, Liz, Lisa, and Shafali, and for to the small RU and NSF for the opportunity to do this research.
All right, let's thank the speakers, sorry. Does anybody have any questions? Could you stop recording in case somebody is afraid to ask a question because they're being recorded?